If we look at what happened when we used the chain rule to find this derivative, we had our function h was the composition of two functions. So the total derivative for h was just the product of the two total derivatives, the total derivative for the function f times the total derivative for the function r. Now f had two outputs, which we called s and t, right? And it had three inputs, so f was a 2 by 3 matrix. If you look at the entries were the derivative of s with respect to x, and the derivative of s with respect to y, and the derivative of s with respect to z. And then the second row in the total derivative df was the derivative of t with respect to x, and the derivative of t with respect to y, and the derivative of t with respect to z. And now the derivative, so that's df, right? And then the derivative dr, since r had two inputs and three outputs, it was a 3 by 2 matrix. And we were calling the entries of r, x, y, and z. So the first entry was dx du, and the second entry was dx dv. And then we had dy du and dy dv. And we had dz du and dz dv. So if we look at the four entries in h, let's see, the entries in h would be the outputs of h are s and t, and the inputs are u, right? So we would have h would have a ds du and a ds dv, and it would have a dt du and a dt dv. So since the original, in this entire chain, you start off with u and v, you end up with s and t. This should be a 2 by 2 matrix like this, right? So this should be the matrix for h. Well, if we look at this, ds du, that's measuring the ratio of a change in s to a change in u. And look at the entries that are involved. You get ds dx times dx du plus ds dy times dy du plus ds dz times dz du. Okay, so if you want to find how s changes with u, just one of these entries, notice what you're doing. You're thinking, okay, here's my function s. It depends on three things, x, y, and z, and each of those depends on two things in general, u and v here. So if I want to think about making a change in u, and how will that cause s to change, what will be the ratio of those changes, I can think about, okay, changing u can change x, and changing x can change s, plus changing u can change y, and changing y can change s, and changing u can change z, and changing z can change s. And that's exactly what this is saying, right? To find ds du, think about how changing u changes x, and then how changing x changes s, and changing u changes y, and changing y changes s. Changing u could change z, and changing z could change s, so we get this particular pattern of derivatives. So if we just want to find a particular entry in the total derivative matrix for the composition, then we can just draw a little tree and show how that particular variable is related back to the originals, and consider these rates of change. We'll just multiply them. That will find the correct entry from the matrix multiplication if we do that. So let's look at an example here. We have this function w is found from x, y, and z. So and x, y, and z are found from these functions of t. So if you look at it, we have t, right? And then this function takes that t and turns it into an x, y, and a z, and then that x, y, and z get turned into a w. So we could ask about how does w change with t, right? Because if we think about the entire composition here, then we have t as the input and w as the output. Well, look at the tree diagram then. W depends on x, y, and z, and each of these depends on t. So if we think about how does w change when we change t, well, changing t can change x, right? And changing x can change w. But changing t can change y, and changing y can change w. And finally, changing t can change z, and changing z can change w. Let's figure out what each of those entries are. dw dx, this is the only place x appears, right, in w. So dw dx would be 2x e to the 2y cosine of 3z. And then dx dt, x is cosine t, so that's going to be minus sine t, plus dw dy. So dw dy, the derivative of e to the 2y with respect to y is 2e to the 2y. So we get 2x squared e to the 2y cosine 3z times dy dt. Y is a natural log of t over 2. The derivative of the natural log is the derivative of the inside over the inside, so we get 1 over t plus 2. And then finally dw dz, and the derivative of cosine 3z is negative sine 3z times 3, so we get negative 3x squared e to the 2y sine 3z, that's dw dz, and then dz dt is 1. So we could use this tree here, where we look at how w depends on these intermediate variables, which then depend on t, to determine what the formula should be. Or we could just go back to the idea that we have, if this is our outside function f, and then these three form a function maybe r, then h is f compose r. So if we say that h is f compose r, then the total derivative of the composition should be the total derivative of f times the total derivative of r. Now f is a function with one output and three inputs, so that should be a 1 by 3 matrix. And r is a function with three outputs and one input, so that should be a 3 by 1 matrix. And the entries here, df dx, are is 2x e to the 2y cosine 3z, and df dy is 2x squared e to the 2y cosine 3z, and df dz would be negative 3x squared e to the 2y times the sine of 3z. Those are the three entries in the matrix total derivative for f. And then the total derivative for r, the entries are minus sine t and 1 over t plus 2 and 1. If you multiply this 1 by 3 times a 3 by 1, you get this 1 by 1 matrix, which we've already found. So whether you think about it as taking the chain rule as multiplying two matrices, or you think about finding individual entries by computing this tree, you're going to get the same answer.